All right, good afternoon to everyone out there in abstract algebra land. This is our likely our last live stream of the semester, where we're going to spend a little bit of time together looking at some final exam review problems. I don't think we'll have the time to be completely comprehensive with this look, but I definitely want to be responsive to whatever questions that you have. If there are particular areas in the course, learning standards that you want to talk more about. We've already had a special request to make sure that we dwell a little bit on the topics of chapters 9 and 10. That is the material on normal subgroups and factor groups, as well as homomorphisms. There's a beautiful story to be told there, so I definitely would like to spend some time there for sure. But any other sort of particular areas of focus that you'd like to see during today's live stream, either drop a question or a comment in the stream chat, or drop a question or an answer in Slack. I'll be looking at both of those places as we go along. We'll try and spend about an hour together here today, maybe an hour and a half. We'll see, and we'll see what kind of progress that we can make. So as we're getting started here, I did prepare some review problems that we distributed in class the other day. Why don't I bring those up real quickly so that we can take a look at those together. Just come and grab those out of my folder. Bear with me for a second here. So that would be this one. Okay. So this was the sheet that you saw in class yesterday. I modified a couple of the problems just to fix a couple of typos. So I think what I'd like to do is let's start with question 1, because there's an opportunity there to get to both Learning Standard 9 and Learning Standard 10. And also that was one of the problems that had a small typo with it in class. So let me grab a copy of that, send it over to my iPad, and then we can get rolling. Oops. Oh, sorry, let me try that one more time. Send it over to my iPad. And I'll put it on the screen here and we'll get going. All right, so here's the problem. The problem asks us to consider a finite group, call it G, and suppose that this is a group that has an onto homomorphism onto Z10. And the change that I had to make here was to add the word onto into this problem. Without that word, the problem, as stated, has some pretty trivial counterexamples, as one of the commenters on YouTube happened to point out after I uploaded the class recap video from our last class. So good catch, random YouTuber. So adding the word onto right here makes this a true statement, and let's take a look at why. So just to kind of diagram out the situation real quickly, we've got a finite group G. We don't really know anything about G other than the fact that it's finite. And then on the other hand, we have Z mod 10. So the additive group mod 10 sitting over here, Z10. Let me just take this opportunity to write in the elements of Z10. Why not? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the operation, of course, being addition mod 10. And the assertion here is that we have a homomorphism phi. And what we're supposed to prove in this problem is that just the mere fact of having a homomorphism from my finite group onto Z mod 10 is enough to guarantee that G has two normal subgroups, a normal subgroup of index 2 and a normal subgroup of index 5. So the question is, where are those normal subgroups going to come from? How are we going to prove that those things must exist just based on the meager information in this problem? So let me highlight here in the statement of the problem a normal subgroup of index 2. Let me try and call that, give that by a name. Let me call that H. And then if we also say there's a normal subgroup of index 5, let me give that a name also. Highlight it in green. Let's go to index 5. Let's call that G. Or sorry, let's call it K. So I have to prove to you, or I suppose on the exam you would have to prove to me, why H and K must exist, only knowing the existence of this homomorphism onto Z mod 10. So the word onto is really a key word here, because what does a homomorphism or a function in general being onto tell me? Well, remember, onto means that every single element in the target space, the target set, which in this case is the group Z10, it means that every element in Z10 is getting hit by this function. And so what that tells me is it tells me that the image of phi is all of Z10. Okay. So we don't know how many times these elements are getting hit. We just know that all of these elements are indeed getting hit. So 0 is getting hit by something. Maybe I'll draw some arrows in here. So 0 is getting hit from somewhere, 1 is getting hit from somewhere, 2 is getting hit from somewhere, 3 is getting hit from somewhere, and so on down the line. So this is what we get by virtue of knowing that this homomorphism is onto. Right? We know that every single element in Z mod 10 is phi of something that came from G. Another important thing to mention is that the image of a homomorphism is always a subgroup of that target group, right? The group on the right, the group that the homomorphism is mapping into. Right? So image of phi is always a subgroup for phi, a homomorphism from G to H. Image of phi is always a subgroup of H, the group that we're mapping into. In this case, that subgroup happens to be the whole thing, right? the whole group Z10 in this example. Okay, so that's an important thing to know. So then the question is, how am I going to use that observation about the image, which is an observation about something that lives inside of the target group Z10, how am I going to pull that information back to tell me something about the domain, the source group G in this example? How is the homomorphism phi going to help me to carry that information from the group on the right back to the group on the left? Well, here's another key observation. We can make the following, and this is probably the key observation that powers all of this work that we do navigating between homomorphisms and normal subgroups. There are a lot of different ways to navigate this, but here's a couple of important ones. So if phi is a homomorphism from a group A to a group B, let's say, then there's a couple things that we can say for sure. On the one hand, we can say that the image of A is a subgroup of B. That much is a guarantee for any homomorphism. Another statement that we make use of a lot in this, the image of phi, not image of A. Sometimes the image of phi is called phi of A, so maybe I'll write that in here also. Right? It's the result of applying my homomorphism to all the elements of A. And that's always a subgroup of B. Meanwhile, the kernel of phi is a subgroup of A. Remember, the kernel is everything that is getting mapped by this function to the identity element in the target group. So if you want, we can sort of draw back here in G a subgroup, call it K, or well, let me call it the kernel, KER of phi, that everything inside of this subgroup is all going to the identity element in the target group. Right? And the kernel of phi is guaranteed to be a subgroup of the source group. In this example, we called it A. But actually, a little bit more is true. Right? that the kernel of phi is more than just any subgroup. It's guaranteed to be a normal subgroup. The left cosets and the right cosets of the kernel are always going to be equal one to another. So the kernel is a normal subgroup of A. But we can say even more than that. And it's this third statement that I think is going to be most useful to us in this problem. And that is that a homomorphism not only associates the entire group on the left, the entire image on the right with a subgroup, but it also associates partial images with subgroups. And what I mean by that is if I have a subgroup, let me call it M, if I have a subgroup of the source group, G, right? In this example, it's A, right? If I start with a subgroup on the left and I apply my homomorphism to it, that result is also going to be a subgroup on the right. Phi of M is going to be a subgroup of B on the right. So that much is going to be a true statement. But then the reverse is also true. So if N is a subgroup of B, then the inverse image of N will be a subgroup of A. So this is the really nice thing about homomorphisms. We were able to make a lot of similar statements like these with isomorphisms. After all, every isomorphism is also a homomorphism. But it's gratifying that these statements about subgroups that were true about isomorphisms remain true even when we get rid of the one-to-one and onto requirement. But in order to get where we're going, we also want to say something even a little bit stronger. And that is, we also want to make a statement about normal subgroups. And the statement that we can make is that we can go backwards with normal subgroups. What I mean by that is if I have a normal subgroup of my target group, then the inverse image of that normal subgroup will be a normal subgroup in the original group, in the source group. And so that's going to be the key observation that we want to use in the course of working on these problems. Let me slow this down for a second because I got a quick question in the Slack channel about why is it that the image of a subgroup is always a subgroup? Can we take that for granted, or do we need to apply a subgroup test or something along those lines? So let me just make a quick comment in the Twitch chat so that we know that that's what we're about to take a quick moment to talk about here. Is the image of a subgroup always a subgroup, or do we need to check that? So let's just take a quick moment and look at that problem, and then we'll come back to where we were. Is the image of a subgroup M, subgroup of A, always a subgroup? So the great thing about abstract math, right, is that if I check this once, if we can prove this theorem is always true, then we don't need to check it every single time. Let's try applying a subgroup test to prove this general statement. If we can do that, then we'll be in good shape where we won't have to go back and reinvent the wheel and reprove this statement every time. So let me pull out the trusty cocktail napkin and see if we can come up with an argument here for why that should be the case. So I'll start here on my napkin by saying, well, what we're trying to do, what we would be trying to do, is show that phi of M, the image of M, is a subgroup of B. So if we want to try using a subgroup test to do that, then what we'd want to do, let's say we try to use the one-step subgroup test, we'd want to show that if X is an element of phi of M, and if Y is an element of phi of M, then XY inverse we'd want to show is an element of phi of M. Well, let's see. Let's try and make the argument. So if x belongs to phi of m, then applying the definition of the image, this would mean that x is equal to phi of, let's say, little m, for some little m in the subgroup M. And then likewise, make the same argument for y. Y would be equal to phi of, let's say, little let's say m prime for some m prime that belongs to the subgroup M. And so then my goal here would be to say something about what I get when I do x, y inverse. So the first thing to ask yourself is, if I take the inverse of the image, so phi of m prime, and then I take the inverse of that element, is that the same thing as if I take phi of the inverse of m prime? Do homomorphisms send inverses to inverses? And the answer to that is yes. This is one of the properties that relies, it's one of the things that isomorphisms did that only relied on the homomorphism property that isomorphisms has. It's like we didn't need one-to-one and onto to prove that isomorphisms carry inverses onto inverses. And for that reason, we can conclude that homomorphisms also carry inverses onto inverses. So we can bring this inverse inside of the parentheses here and say that y inverse is the same thing as my homomorphism applied to m prime inverse. Sorry, I'm putting the prime and the inverse next to each other. It's a little bit hard to read, but okay. And then when I multiply these two things, x times y inverse, what I'm going to get is I'm going to get phi of m, that was my x, right, multiplied by phi of m prime inverse, but now what can I do? Now I can remember that phi is a homomorphism, and therefore it satisfies the homomorphism property that lets me combine the product of the phi's into phi of the product. And so what I get here is phi applied to m times m prime inverse. Right? That is the homomorphism property. That's all that we know about phi, right? Is it's a function from the group A to the group B that satisfies the product rule property that lets me recombine these two things together. So now the question is, do I know that this element belongs to the image of the subgroup M? I do if and only if I know that this element, m times m prime inverse, is an element of the subgroup M. But that is indeed true, that this thing inside here belongs to M because M is a subgroup of G, or of A, because M is a subgroup. And therefore M satisfies the one-step subgroup test also, and so any element of M multiplied by the inverse of any element of M will remain inside of M, just by closure. And therefore this belongs to phi of M as desired. Okay. So the image of a subgroup is always a subgroup. So that is something that we can take for granted. We don't have to reprove that any given time. So here the answer is yes. Right? Okay, so the image of a subgroup is always a subgroup. We can take this for granted as a theorem about homomorphisms. So let's go back to where we were on this problem. So the image is going to be a subgroup, always. Right? And that's true not just of the image of the entire group, but the image of any subgroup is going to be a subgroup. But then the really cool fact is that it goes backwards the other way, right? The pre-image, the inverse image of any subgroup is a subgroup. But that we can also add the word normal into that and find out that that result still holds true. So let me back up a second and ask the question about going forward. So let's suppose that I had a normal subgroup. So suppose that M is a normal subgroup of A. Is it true that the image is a normal subgroup of B? So we already know that the image is going to be a subgroup, but does a homomorphism necessarily carry normal subgroups onto normal subgroups? To figure that out, let's add one more napkin onto my page here and see if we can't come up with a reason, either a reason to believe this statement or maybe a reason to disbelieve this statement. So let's see what we might get here with the second napkin. So if I want to know whether or not phi of M is a normal subgroup of B, so this is going to give me a chance to talk briefly about topic number 9, which is also a good thing for this problem, right? If I want to show whether or not phi of M is normal in B, one of the ways of doing that is to show that phi is a closed subgroup under conjugation by any element of the group B. So I would have to show that for any little b in my group, that B multiplied by phi of M multiplied by B inverse is at least a subset of phi of M, right? And it turns out that if it's even a subset, then we also get that it's equal, just because of how cosets work. That the coset is going to be in bijection, and so a subset which is in bijection must be equal to the whole thing. So let's see if that's necessarily going to be true. If I pick an element in this first set, then that means that that element is equal to B times phi of little m times B inverse for some m from my original subgroup M, right? And so the question is, do I know that this element x is going to also be in the image of M? Can I know for sure that this is equal to, question mark, equal to phi of, let's say, M prime for some M prime in M? So we have to somehow be able to use this observation that that M is a normal subgroup of A. But the problem is that this B is potentially coming from something that phi is not hitting inside of the target group. And so looking at this, I sort of get heartburn and say, maybe this isn't true, maybe not true, if B doesn't belong to the image of my homomorphism. So with that suspicion in my mind, I'm going to try and go back to the bigger napkin for a second and see if we can write down a counterexample. So the counterexample I've got in mind would be one in which I have a group on the left that has a bunch of nice normal subgroups, and maybe a group on the right that doesn't have any nice normal subgroups. So if I'm thinking about groups that don't have nice normal subgroups, the first one that comes to mind would be either a dihedral group, where there's really only a couple of normal subgroups to choose from, or better yet, I could pick a simple group on the right side. That would be a group that has no non-trivial proper normal subgroups. Just to keep the algebra a little bit simpler, let me choose a dihedral group. Let's say it's a dihedral group with a square. I'm going to write the word square here so that we don't confuse D4 with D8, as we have sometimes done in the past. So the dihedral group with a square, and then maybe over on the other side, I'll pick, let me pick Z2. So super nice additive group of integers mod 2. And then over here on the right side, I get D4, and that's got these 4 elements that together form a subgroup of rotations. And then I also have T, TR, TR squared, and tr cubed. So there's all my elements for D4. And so what I'd like to do is I'd like to try picking a homomorphism from Z2 into D4. And the homomorphism I choose, first of all, we know has to send the identity to the identity, so there's really no choice there. And since 1 in Z2 is an element of order 2, that means that whatever I send 1 to in D4 has to be something whose order is a divisor of 2. This is another super useful statement about homomorphisms that we didn't take the time to prove, and I'm kind of wishing that we had, because it's a really useful fact. So at this point, let's put that fact on the table. If phi is a homomorphism, then phi of g divides, the order of phi of g divides the order of g. Right? So in this example, that means that wherever I send 1 to, I can either send it to the identity or I can send it to something else that has order 2. So let's suppose that I decide to send it to T, which is a reflection, has order 2 as an element of the dihedral group of the square. So now the idea is, first of all, to check that this actually is a homomorphism. And to check it's a homomorphism, we just need to check to make sure that the product rule is satisfied. And the only products we can take in Z2 are 0 plus 0, and that's getting sent to E plus E, which is E, or so E composed with E, which is E, that's fine. 0 composed with 1 is getting sent to E composed with T, which is getting sent to T. 0 plus 1 is 1, so that's fine. 1 plus 1 is 0 in Z mod 2, and T composed with T is the identity, so the homomorphism property is indeed satisfied by this function. So this function is a homomorphism. So the question is, what is my normal subgroup that I want to look at? Well, the normal subgroup I want to look at over here on this side is the whole group itself, Z2, as a normal subgroup of Z2. That's normal. Every entire group is a normal subgroup of itself. That's always true, because it is its only coset, and therefore its left cosets and its right cosets are all just equal to itself by closure, and hence equal to one another. So the whole group over here is a normal subgroup. But what's the image of this group going to be? The image is going to be the subgroup that consists only of E and T. But we've convinced ourselves previously that it is not a normal subgroup of D4. After all, for example, Rn and Nr are going to be different. Rn is going to be R with Tr cubed, and Nr is going to be R with Tr. So this is an important observation about how homomorphisms interact with subgroups. Homomorphisms always take subgroups onto subgroups, and conversely, going the other way, the inverse images remain subgroups. So subgroups always get associated with subgroups. But normal subgroups over here do not necessarily get associated with normal subgroups over there. Normality is only preserved going backwards, taking an inverse image. So just to kind of write that conclusion up here at the top of the screen so that we don't lose it. A homomorphism always sends subgroups to subgroups, going either way. So that one's a bidirectional association. But the normal subgroup association only goes one direction. It goes the preimage direction. So only when I have a normal subgroup of the target group and I take the preimage am I guaranteed to get a normal subgroup of the source group, the domain, if you like. Right? This is the kind of a common thing that happens when we study functions and sets, and when you go and study things like topology in a course like real analysis. This is a common sort of symmetry that gets broken for things like if phi is a continuous function and I have an open set of my domain or an open set of my codomain. Continuous functions don't preserve openness of sets when they go forward, but they do preserve openness of sets in the inverse image. So this is just another example of some properties that are preserved only going one direction across a function. So coming back to the problem that we started with. We know that if I have a normal subgroup here in my target group, that its inverse image is going to be a normal subgroup back in the domain, back in the source group. And so it would seem like what I would need in order to have a normal subgroup of index 2 and a normal subgroup of index 5 inside of G is I would have to have a factor group. So now here's a good time for us to bring in a factor group. If G has a normal subgroup of index 2, so if H is my normal subgroup of index 2, if G colon H equals 2, then G mod H, the factor group, this is the group whose elements are the cosets of H and G. This would have to be a group of order 2 on the one hand. Right? But on the other hand, the first isomorphism theorem would tell me that I can produce G mod H, group of order 2, if I can produce a homomorphism whose image is a subgroup of order 2 on this side. So if I can realize H as the kernel of a homomorphism, so kernel of phi, G mod the kernel of phi would be a group of order 2. I can do that if and only if, and according to the first isomorphism theorem, the image of phi is a group of order 2. So the question is, since the image of phi has to be a subgroup of my target group, does my target group have a subgroup of order 2? And the answer to that question is yes. So here now we finally get to the arc of how this proof might go. Right? I start over in my target group and I make the observation that my target group Z10 has a subgroup whose order is 2. Right? Namely, the subgroup consisting of the elements 0 and 5. So if I can show that there exists a homomorphism from G onto Z10 whose image is this subgroup 0 and 5, then the inverse image of that is going to be what we're looking for. Well, let me give myself some room here so that we can kind of flesh out this argument. And then I want to have time to also talk about a couple more of these problems by way of review. But this one's a good one because it touches on a lot of different connected ideas that we have toward the end of our course. So let me get another napkin out here. And we can kind of figure out how we want to say this. So the first thing I'm doing here is I'm making the observation that Z10 has a subgroup of order 2. Has a subgroup. Let me call that subgroup, let me call it X, 0 and 5, whose order is 2. But we also know something else about this subgroup. We know that this subgroup is a normal subgroup. And so you stop and think for a second and say, well, how do we know that that 0, 5 is a normal subgroup of Z10? Well, it's a normal subgroup because Z10 is an abelian group. And every subgroup of an abelian group is going to be normal automatically because the left and right actions of any element on that subgroup are just going to be identical to one another on an element-by-element basis. So of course it'll be true on a setwise basis, which is what we need for a normal subgroup. So this is not only a subgroup, it's a normal subgroup. But then there's something else that we also know. We also know for sure that my homomorphism phi, given to be in the problem, is an onto homomorphism. So it also means that X is a subgroup of the image of phi, because the image of phi is the entire subgroup Z10, right? So what that means is that if I look at the inverse image of X, so the inverse image of X would include all the elements that map to 0, but it would also include all the elements that map to 5. And so these two blobs here taken together would form the inverse image of my subgroup X as a subset of G. Right? So phi inverse of X is going to be a subgroup of G. All right, so what else can I say about phi inverse of X? I know it's a subgroup of G because every inverse image of a subgroup will, under a homomorphism, will always be a subgroup. But because I knew that X was not just a subgroup, but a normal subgroup, that allows me to say, according to what we've been talking about, that this inverse image is also a normal subgroup of G. And that is a super useful fact, right? Because what that tells me is that I can form the factor group G mod the inverse image of X. So this red and purple blob taken together form a normal subgroup of G, and if I take the factor group of G by that normal subgroup, what I get, according to the first isomorphism theorem, so there's the key sauce here, first isomorphism theorem, what I get is going to be something which is isomorphic to the image. Wait a second. If I were to take the, what did we say here? If I take the inverse image of X as a normal subgroup, how do I want to say this? I guess, so the question that I'm asking here is, what, if anything, can we say about the cosets of the kernel of this homomorphism? So now thinking of G as being a homomorphism restricted to phi inverse of X. It's sending everything in the red blob is going to 0, and everything in the purple blob is going to 5. Right? And these are going to be cosets one of another. So this purple blob here is going to be a coset of the kernel of phi. So if I pick an element in there, let me call this element little g or something, then this purple blob here is going to be G times the kernel of phi. And so what am I going to get out of this here? I'm kind of talking myself in circles. Tell you what, I've got to go look something up real quick. I'm going to come back to this live stream in just a second, and we'll wrap up this problem. So I'm just going to pause the stream real quick. I'll be back in just a minute. Thank you, Slack channel. Yes, my audio was having some issues there. So let me just rewind for a second and recap what I just said. So the key element here is that the index of 0, 5 as a normal subgroup of Z10 is 5. Right? Maybe if I can draw a different diagram, I think it might help to illuminate what's going on here. So in Z10, we've got this normal subgroup, 0, 5, that has 2 elements, but its index in Z10 is 5. We can see that just by looking directly at the cosets. 9, right? So there's 5 cosets inside of Z10. And what we're doing in this homomorphism is that we're looking back in the group G, which we don't really know much, if anything, about. Right? But what we're saying is that this 0, 5 is, in fact, a normal subgroup of Z10. So what did we call this? On the other screen, I called this X. Right? X is a normal subgroup of Z10. And for that reason, its inverse image as an element of G, as a subgroup of G rather, is a normal subgroup, in fact, of G. And this is this subgroup that I'm trying to call this subgroup here K. Right? And so K is the inverse image of X. And so all of K gets mapped to X by this homomorphism. And we know, based on our theorem about homomorphisms, that this is going to be a normal subgroup of G. So that much we know for sure. But then the other thing that we can say is we can say what the index of this normal subgroup inside of the group G is going to be, because each one of its cosets is going to get mapped to one of the cosets of Z10 in a fashion that's 1-to-1 and onto, because phi is 1-to-1 and onto. If phi were not onto, then some of these cosets here would get mapped to, some multiple of these would get mapped to the same coset over here on the right side. But because phi was onto, we know for sure that each of these cosets is going to have come from a distinct coset back here. So there's going to be an onto correspondence of these cosets as well. And so for that reason, the index in G of my normal subgroup K over here is going to be 5. And so that's the index 5 subgroup that we were looking for. If we wanted to take that a step further, we could also say that the factor group, G mod K, so its elements are going to be these cosets, K itself, and then the 4 other non-trivial cosets of K. This is going to be a group of order 5. And there's only one group of order 5 up to isomorphism. That means that G mod K has to be isomorphic to the cyclic group Z mod 5. So that's what's going on with this problem. Sorry for the technical glitch there for the moment. I want to move on to do another couple of examples. Before I do that, are there any questions or requests for where we go next as I'm getting my papers together? So let's take a quick look back at our final exam review sheet. I'm going to try to pick one that gives us the opportunity to talk about something we haven't yet talked about. So how about we find, okay, let's take a look at, problem 8. Do I like problem 8? kind of also want to pull in something that lets us talk about cosets some more. Maybe, well, let's start with problem 8, and then we can maybe move on from 8 to find a way to get cosets into the mix too, just because there's kind of two, I feel like the two learning standards at the end of our course that people still want the most additional practice with are the standard about cosets, that's standard 7, and then also the standard about isomorphisms, standard 6. So if we have an opportunity to kind of look at both of those together, I think that could help as we sail into the final exam here. So let me just take a moment to get this problem over onto my canvas. And then we'll move forward. iPad. And get this moved in here. All right, so here's the problem. The problem asks us to list every possible isomorphism from Z8 to Z8. So if you like terminology, and we all should, what we're really doing here is listing the elements of the automorphism group of Z8. Automorphisms, remember, are just isomorphisms from a group to itself. So in this problem, what we're really doing is we're trying to find the group structure of the automorphism group of Z8 and also the automorphism group of Z12. So let's start with Z8 and think about what do we know about Z8 and what do we know, more importantly, about isomorphisms. So if I did have an isomorphism from Z8 to Z8, let's kind of think of these. I'm going to use the clock metaphor this time. Z8 to Z8. And so each of these, I'll just write one out first. Each of these can be thought of as clock face, 6, 7. Remember, addition is the operation on this group. And so I'm trying to find isomorphisms from one of these clocks back to itself. Right. And so anytime we're trying to list isomorphisms from a group to itself, the first most obvious example is the identity function, e of x equals x. Right? The function which just sends every element to the same element in this group. Because these groups are not only isomorphic, they're actually the same group. It's really natural to define this sameness function, which trivially ends up being an isomorphism. So that, of course, would just be the function that associates 0 to 0, associates 1 to 1, 2 to 2, 3 to 3, and so on and so on and so on. So when we're listing out the elements of the automorphism group, that function, e of x equals x, is going to be one of our elements. And because when I compose any other function with the identity function, I get that same function back, that means that this function, the identity function, is also the identity element in the automorphism group. So that's always a good place to start. The question is, where do we go from there? How else can we make, besides the identity function, how else can we make an isomorphism from Z8 to Z8? And so the key observation is that because Z8 is a cyclic group, it has some generators. Specifically, we can take 1 as one of its generators. And any isomorphism from a cyclic group to itself necessarily has to carry a generator to a generator. Right? Both of these groups are cyclic groups. And we have to send generator to generator. One of the reasons that we know that that has to be true is we know that isomorphisms preserve order of elements. They also preserve the orders of the group, right? And so a generator in this group over here is going to have order 8, and therefore its image under an isomorphism will also have to have order 8, right? because isomorphisms preserve the order of elements. So if I'm trying to figure out how to make more isomorphisms, what I'm really asking, the question I'm really asking, is where else can I send the generator 1 besides sending it to 1, which is what the identity function did. So now is a good time for us to ask, what are the other generators of Z8? And that's a question that gets answered. Generators of Z8. This is the same thing as the relatively prime residues mod 8. So relatively prime to 8. In other words, the generators of Z8 can be found as the elements of the group U8. Right? All of the numbers that are less than 8 would are relatively prime to 8. And so those numbers are 1, 3, 5, and 7. So those are all of my generators for the group Z8. Let me highlight them on the clock face here. 1, 3, 5, and 7. And any isomorphism between these two groups is going to send 1, which is a generator of Z8, to one of these 4 generators of Z8. But every different choice that I make there is going to give me a different isomorphism. So let's say I make the choice to send 1 to 3. An example of a homomorphism that does that is phi of x equals 3x as a homomorphism of Z mod 8. I'm going to call that phi 1. So that's going to be a homomorphism of Z8, but because it sends a generator to a generator, that also makes it an isomorphism of Z8 to itself. So the tripling function will be an automorphism of Z8. And likewise, if I decide to send 1 to 5 instead, that suggests a quintupling function, phi 2 of x is equal to 5x. I'm using multiplication here to define these homomorphisms because multiplication distributes over addition and therefore will satisfy the homomorphism property of these additive groups. So the function which multiplies by 5 is also going to be a homomorphism, but because it sends generator to generator, will also be an isomorphism for these two groups. And then finally, the function which multiplies everything by 7. We'll send this generator to that generator and be yet again another different isomorphism from Z8 to itself. And so if you kind of squint at these 4 automorphisms, you find out that each one of them can be defined by, well, what am I multiplying by? Right? I'm multiplying by 1 in this automorphism, I'm multiplying by 3, I'm multiplying by 5, I'm multiplying by 7. So it turns out that this group here, this group which is the automorphism group of Z8, we've said what its elements are. But if we think about how these functions would compose one with another, let me just take a moment and ask, like, what function would I get if I were to do, I don't know, phi 2 composed with phi 3, right? Phi 2 composed with phi 3 means phi 2 of phi 3 of x, right? But if phi 3 of x is 7x, and phi 2 of x is 3x, and so this is going to be 3 times 7x. I'm just going to kind of write that as 3 times 7. But in U8, 3 times 7, that's 21, which if we reduce it mod 8 is 5. These functions compose together in exactly the same way that these numbers 1, 3, 5, and 7 multiply together, because composition of these functions is the same thing as multiplication by their coefficients. So what that does is it not only tells me that the elements of G are these 4 functions, it also tells me that the group structure of the automorphism group of G is isomorphic to the group structure of the multiplicative group of units mod 8. Right? So not only is it true that the elements are the same as U8, or have a correspondence with U8, but it also shows that the group itself is isomorphic to U8, which is going to be a super valuable observation here in just a moment. Question quick came up on Slack. How did we get 5x from 3 times 7x? Why is 5x equal to 3 times 7x? Because mod 8, 3 times 7 is 21, which is congruent to 5 mod 8. After all, 21 minus 5 is 16, which is a multiple of 8. Right, so I'm just doing my arithmetic there, mod 8. So this is a super valuable observation because what it does, if we believe the observation in general that the automorphism group of Zn is isomorphic to Un, for the reasons that I just sort of explained, even though I didn't write down the proof here, the correspondence is that every one of these automorphisms is just going to be phi of x equals multiplication k times x, and that k is going to get associated with one of the elements in Un. So that's the nature of the isomorphism, careful now, the isomorphism between the automorphism group of Zn and the multiplicative group of units Un. If we believe that this is true, then that means that G, which is the automorphism group of Z8, is isomorphic to U8. And now is the time that we, because we have taken a lot of care this semester to learn a lot more about the U groups, and we know, based on what we know about the U groups, that U8, it's a group of order 4, but it's congruent to, it's isomorphic to, the direct product of Z2 with Z2. So that's using a fact from chapter 8 about the U groups, that because 8 is a power of 2, we have a theorem that tells us that U8 is isomorphic to the direct product of the Z2 with Z to 2 to the power of the exponent of 2 minus 2 here, so it's 2 to the power 1. So we have a theorem that tells me that U8 is isomorphic to Z2, direct product Z2. And the benefit of this is if I now go and ask the same question about Z12, we'll know that the automorphism group of Z12 is isomorphic to U12. And knowing what we know about the U groups, once again, we can say that U12 is not just isomorphic, but equal to, I suppose I should say isomorphic, equal to U4, internal direct product U3. So there's a subgroup, a normal subgroup of U12 that's isomorphic to U4, a normal subgroup of Z12 that's isomorphic to U3. Their intersection is trivial, and together their product forms the whole group, U12. But then again, we can use that same theorem to convince me that U4 is isomorphic to Z2, and U3, since 3 is prime, it's a power of an odd prime, its U group is isomorphic to a cyclic group. And we can reduce that down to Z2 plus Z2. And so at the end of the day, we find out that the automorphisms groups of Z8 and Z12, both of them are isomorphic to the Klein 4 group, Z2 plus Z2. And therefore, yes, they're isomorphic one to another. So if we think about all of the different isomorphisms from Z8 to itself, and we think about all the different isomorphisms from Z12 to itself, those two groups, those automorphism groups, are isomorphic one to another. There are exactly as many automorphisms of Z8 as there are automorphisms of Z12, and they interact with one another in all of the same ways. So those two groups are isomorphic. So we could also have pulled in the fundamental theorem of finite abelian groups into the mix. If we didn't know exactly how to reduce U groups into isomorphism classes of direct products of Z groups, if we didn't know that, then we might have proceeded just by saying, well, once we know that there's 4 elements in this group and 4 elements in that group, there are 4 automorphisms of Z8, 4 automorphisms of Z12, and if we know, according to the hint that I gave you, that both of those groups are abelian, which, by the way, there's no such thing as a non-abelian group of order 4, right? Then that would give us, according to the fundamental theorem of finite abelian groups, if I knew that both of my groups had order 4, I would know for sure that there's only two options for the isomorphism class of what those groups would be: a cyclic group of order 4 or the Klein 4 group, Z2 plus Z2, sometimes called the elementary group of order 2. And so then if I wanted to know which one each of these automorphism groups were, I would just need to determine whether or not we can find an element of order 4 in these groups, or whether all the elements have order 1 or 2, which is what would be the case over here. But because of what we knew about U-groups from our work in Chapter 8, we didn't have to go that route. We could just directly transform the U's into isomorphism classes of direct products of Z's. Are there questions about this example? I want to go forward and do one more example before we wrap up the stream today to try to pull in the last of a couple more learning standards. All right, so let's wrap up by looking at problem 4 on our review sheet. So problem 4 is a problem that asks us to start by considering a non-abelian group of order 8. And then we have to show that there's no way to write it in any nice way as an internal direct product, unless that internal direct product were trivial. So let's take a look at that together. And that'll be our last example. This one I think will go a little quicker than the previous examples that we've done, for reasons the appreciation of which I think are good for us to remember. So here's the problem. Get it onto the canvas here. There we go. So the problem is, suppose that I have a non-abelian group of order 8. What's nice about this problem is that we don't have to know anything else about G. That sort of it limits us. So there's only a short set. There's only a very small list of non-abelian groups of order 8, and it doesn't matter which one of them they are for this problem. So the question says, if I have two normal subgroups, H and K, of G, such that G is an internal direct product of H and K, then what we want to prove is that either H has to be trivial or K has to be trivial. So there's no way of writing G as a non-trivial internal direct product if G is a non-abelian group. So anytime we're talking about internal direct products, I always like the sort of the pictorial way of approaching it. So suppose that this is my group G. And suppose that suppose that neither H and K were trivial. So let's start with that assumption by way of contradiction. So say that H and K are both non-trivial. So I'm going to make an argument by contradiction. Then let's take a moment to think about what H and K would have to be. On the one hand, let's suppose that one of them were trivial and that G was the internal direct product of H and K. If one of these were trivial, it would mean that the other would have to be the entire group G. Right? So if H and K are both non-trivial, that is going to imply that not only are they not equal to the trivial group, but they're also not equal to the whole group, right? Because if one of them is the whole group, the other one has to be the trivial group if their internal direct product gives me all of G. So what this means is both H and K are intermediate sized, right? They're proper non-trivial subgroups. So what do we know about them based on that fact? Well, if they're subgroups of G, then according to Lagrange's theorem, the order of G, sorry, the order of H and the order of K both have to be divisors of 8. And so Lagrange is going to tell me that the order of H and the order of K have to be divisors of 8. 1, 2, 4, or 8. But H and K are not trivial, so their order can't be 1. And if H were trivial, then K would have to be the whole group and vice versa. And neither of those are true. Therefore, H and K can't have order 8 either. So what that tells me, what my contradictory assumption here tells me, is that H and K have to respectively have order 2 and order 4. Like one of them's got to have order 2, the other one's got to have order 4. And without loss of generality, let's assume that the order of H is 2 and the order of K is 4. Because if it were the other way around, we could just reverse the roles of H and K in my proof, and since an internal direct product is symmetric up to isomorphism, it's actually better than symmetric up to isomorphism, actually symmetric on the nose, I would have the same proof at the end of the day. So let's just declare that H is a subgroup of order 2, K is a subgroup of order 4, and let's kind of try to fill out our picture here. So what I would have is I would have these two cosets of K, right? So here K would be my first column in my chart. In my chart showing the elements of K, or of G rather. All right, so here's K. And then I would also have H, which would have 2 elements. So I'd probably write those on the first row here. H. Let me write that out here. And of course, if G is the internal direct product, it means that the only overlap between H and K has to be the identity element. And so this is always the picture that we have in an internal direct product. That's the definition of internal direct product. And it would therefore mean that I can account for the entire group in 2 ways. I can account for the entire group as being made up of partitioned by the 4 cosets of H, or I can account for the entire group being partitioned by the 2 cosets of K. Right? And there's my group. So why in the world can this not happen? Right? We're making a contradiction argument. So why is this picture impossible for the group G that we have here? Well, now is a good time to remind ourselves by the fundamental theorem of, well, not even the fundamental theorem. We don't need the fundamental theorem. We know that H is a group of order 2. What do we know about groups of order 2? Well, most important thing to know is that there's only one up to isomorphism. There's only one group of order 2. There's only one way to make a Cayley table with 2 elements up to isomorphism, right? I can give the elements different names if I want to, but I can't get a different algebraic structure. I must get something which is isomorphic to the cyclic group Z2. Right? In particular, H must be abelian, right? Because it must be isomorphic to the cyclic group Z2, and every cyclic group is abelian. Z2 is abelian. Okay, so we know H has to be abelian. What about K? Well, up to isomorphism, there are 2 groups of order 4. Up to isomorphism. One of them is Z4. The other one is Z2, direct product Z2, the Klein 4. Right? So there's only 2 groups of order 4, but both of them are abelian. And so we know for sure that K is going to be an abelian group. So the key observation here is that if I have a non-trivial internal direct product that makes up my group G, in order to be non-trivial, it has to be an internal direct product of a group of order 2 with a group of order 4. But every group of order 2 is abelian. Every group of order 4 is abelian. And what do we know about a direct product of two abelian groups? Any direct product of two abelian groups will have to be abelian. Thus, H, internal direct product K, must be abelian. In other words, because in this example, the internal direct product is a group of order 8, it being abelian would mean that it has to be isomorphic to one of Z mod 8, Z mod 4 direct product Z mod 2, or Z2 direct product Z2 direct product Z2. But all of those examples, importantly, are abelian. And that gives us a contradiction to the assumption that we began the problem with. Right. So here there's kind of a couple of key observations. The first one is that, probably the most important one really to power our analysis, was that every group of order 2 and every group of order 4 is necessarily abelian. And the second key assumption, the observation rather, is that the direct product of two abelian groups must always be an abelian group. And so there is no way to write a non-abelian group of order 8 as an internal direct product, unless that internal direct product were trivial. So that's what we get out of this contradiction, is that we made the contradictory assumption that H and K were both non-trivial. That assumption cannot be sustained because it implies H cross K is abelian, which is not true. Thus, we can conclude that one of H or K must be the trivial group. Thus, either H is trivial or K is trivial. And that concludes the proof. Any questions about that proof to wrap that problem up? And that's going to wrap up our live stream today once we're satisfied with this. All right, we're going to call that one a wrap then for today. But thank you all for participating in today's stream. If you have further questions that I can shed light on as you're doing your studying between now and the exam tomorrow, feel free to drop them to me in Slack or in an email, but Slack is probably easier. And then I'll see you at the exam.